Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today our two topics are going to be concavity and points of inflection. So we're going to talk about, whether you know about concavity, whether you could define that, whether you know what a point of inflection is already. We're going to talk about how we can identify those things in the original function based on first and second derivatives. So to start off, I'm going to draw a graph of what we'll call f of x, so the original function. Let's go ahead and sketch that. We'll say it continues onwards, but I'm only going to sketch it over that interval. And what I want you to do is sketch the graph of f prime, and then go ahead and try to sketch the graph of f double prime. You can fill in any markings on the x or y axis that you'd like. Again, this is just a sketch, so we're just going to get an idea of what those graphs would look like, and then talk about the relationships between all three of them. All right, so let's first sketch a graph of f prime. And to do that, maybe you want to take note of a few different things, right? Maybe you want to note that there's a maximum here, a minimum here in our original function. So our graph is going to hit the x-axis, right, at those 2 points. Our derivative is going to be 0 at a relative min or maximum, as long as the function is differentiable, and right here it is. There are no hard corners. Now let's think about what's going on with the function before we get to this maximum right here. Well, the function's increasing, which means our derivative is going to be positive. And if we eventually need to end up on the x-axis, right, we can call this A and B. If we eventually need to end up at A, and our function's positive, well, our function's going to be decreasing. So it's going to be decreasing to A. Now, after our maximum at x equals A, our function is decreasing, which means our derivative needs to be negative. And our derivative is going to be negative all the way until B, because that is when our function stops decreasing at B. So essentially, we're going to have something that looks like this. And then we also know that our function is increasing after B, so our derivative has to be positive. So we're going to get, again, something that looks like this in blue. All right, let's think about our second derivative. Do that one in purple. So for our second derivative, let's take a look at our first. Well, our first derivative is decreasing. Maybe we'll just call this point C. It's decreasing until C, where it has a minimum. So we know that it's going to hit the x-axis at C. And before C, well, the derivative is decreasing. So our f double prime function should be negative, right? If our derivative is decreasing, our second derivative should be negative. And then after C, our derivative is increasing, so our second derivative should be positive. So we're just going to have a graph that looks like this. It's going to be a linear graph. And now let's start to talk about what's going on over some different intervals. So if I take a look at my original function f of x, there seems to be something the same about the graph to the left of C and to the right of C. All right, and this is where concavity comes into play. To the left of C, we have a graph that we consider concave down. You know, it looks like an upside down bowl or an upside down hole. And on the right, we have a graph that is concave up. And again, it just looks like a bowl or a hole. And we'll notice that the derivative and the second derivative are going to be doing things here that will hold true whenever a function is concave up or concave down. So let's first take a look at the first derivative. Well, as we travel along the red function, right, when it's concave down, what is happening with our derivative? All right, let me just draw in some tangent lines here. Well, our derivative starts off positive, right here. Then it gets less positive. Then it goes to 0. Then it becomes negative and more negative until we get, again, to right where C is. Then it starts to change. So what's happening, right? What's happening with all these derivatives? Well, the derivatives are decreasing. They start off positive, they get less positive, then they go to 0, then they get negative, then they get more negative. So if we have a function that's concave down, let's do a different color. Let's do orange. So if we have a function that's concave down, 1, we know that we'll just say f of x. F of x is concave down. We know that f prime of x is decreasing. Now notice this doesn't mean it's always negative or it's always positive. If I look at my f prime of x graph to the left of C, well, sometimes it's positive, sometimes it's negative. But as I approach C, my derivative is decreasing. It is first very positive, it gets less positive, it goes to 0, then it gets more and more negative. Let's look at what's going on with our f double prime graph. So again, to the left of C, right? Well, as I approach C, my f double prime graph is, well, it is increasing and it's negative. So it's increasing and it is negative. And what we're going to pay attention to is the fact that it is negative. So f double prime of x is negative. So those are the two things you can pay attention to or look for if you want to know where f of x is concave down. Let's now look at where it's concave up. So we're looking at the points to the right of C. Well, let's start to draw some tangent lines. Right? Tangent line right here, slope is negative. Tangent line right here, slope is negative. Then we have a slope of 0 at our minimum. Then we have a positive slope. And then we have a slope that is even more positive. So the tangent lines go from negative slopes to less negative, to 0, to positive, to more positive. Well, if we look at our derivative graph, we can see that f prime is always increasing when f of x is concave up. So f prime is always increasing when f of x is concave up. Notice again that it could be positive or negative. The key is that it is increasing. If we look at f double prime, we notice that it is increasing, but more importantly, it is always positive. So f double prime will always be positive when our first derivative is, when our original function is concave up. And you may be wondering, well, why aren't we paying attention to the fact that f double prime is increasing? Well, the problem is it's increasing when our f of x function, the original function, was concave down, and it was increasing when it was concave up. So that's not telling us the difference between concavity. It's not giving us any clues as to whether the original function is concave up or down, because if it can be increasing regardless of whether the original function is concave up or down, well then that doesn't tell us anything about the original function. So that's why we're leaving that off, and we're just paying attention to whether f double prime is positive or negative. Now, there is another thing we need to talk about, and that's a point of inflection. Notice this point C that we keep referring to, right? That's how we broke up our concave up and concave down. Well, this point right here is what we call a point of inflection. This is where the concavity switches. Okay, it's where the concavity changes from either concave down to concave up or concave up to concave down. Now, if the function is differentiable at that point, right, well, then f prime is going to have a minimum or maximum at that point, right? If we look at x equals c on our derivative, we have a minimum here. Now, it could be a maximum if we had gone from concave up to concave down. And our second derivative, as long as our first derivative is defined, will be equal to 0. Now, it could be undefined if our first derivative, has a hard corner at its minimum or maximum. But in this case, f double prime is going to be equal to 0. We'll talk a little bit more about points of inflection later, but I hope this gives you a little introduction to concavity and what we can look for in the first and second derivatives when we're talking about concavity. So this is going to be important, especially the second derivative part of this, because what we're going to fill out next is the second derivative test for concavity, which means we're going to test and see what the second derivative is to tell us whether the original function is concave up or down. So it's good to understand what's going on with the first derivative. And honestly, we've done this relationship before with original functions and first derivatives, right? If the original function is decreasing, well, the first derivative is going to be negative. If the original function is increasing, the first derivative is going to be positive. The same relationship holds true with the first derivative and the second derivative, because you can treat those like an original function and the first derivative. So let's get rid of this and let's fill in our formal definition table. So this is what we call the second derivative test for concavity. If f double prime of x is greater than 0, then f of x is concave up. And if f double prime of x is less than 0, then f of x is concave down. So this allows us to find intervals of concavity, right? If we have those little number lines, right, where we find the critical points, except now we would be finding the critical points of the second derivative, right? We'd be doing f double prime of x. And let's say we had critical points at 3 and 6, and then we had positive, negative, positive. Well, we could say f of x is concave up on, right, the interval negative infinity to 3, union 6 to infinity, because those are the intervals where f double prime is positive. And then we could do the concave down interval. That would just be from 3 to 6, because f double prime is negative. Okay, let's do some practice. Take a minute, pause the video, and work through number 1. That's what I just showed you with that table is almost exactly what you're doing here. So you're going to need to figure out where the second derivative is positive or negative, and then write the intervals of concavity for the original function. All right, so we clearly need to find the second derivative first, and I'm going to do that by first finding the first derivative. So f prime of x is equal to 5x to the 4th minus 5. My second derivative, again, just a power rule, is going to be equal to 20 x cubed. So to find the critical points of my second derivative, I'm going to set it equal to 0. It's never going to be undefined, so I don't have to worry about spots where it's undefined. So I'm going to get 0 is equal to 20 x cubed, and that means x is equal to 0. So I only have one critical point. It's at x equals 0. My original function is defined for all x values, so that's why I can go to negative infinity and positive infinity. And, well, my second derivative is also defined for those values as well, so I can also include it. Let's now choose some test points. So let's do f double prime of negative 1. Well, that's going to give me 20 times negative 1 cubed, which is going to be negative 20, so it's negative on that interval. And f double prime of positive 1 is going to give me positive 20. So it is positive on that interval. So now we just need to write our conclusions. We can say f of x, and you do want to specify what function you're talking about, right? You just don't want to say concave up and concave down on this interval, because are we talking about the original function, f prime, or f double prime? Well, we're checking the concavity of the original, so it's f of x. So f of x is concave up on the interval 0 to infinity, because f double prime of x is greater than 0 on this interval. Looks like I'm going to run out of space here. And then I can say f of x is concave down on the interval negative infinity to 0, because f double prime of x is less than 0 on this interval. So you need the justifications as well as the intervals. All right, let's get rid of this. We're going to skip number 2. You can try that one on your own, or we might do it during class. And we're going to jump down and talk more about points of inflections. So what you can do, it says draw dashed vertical lines on the function where the concavity switches from concave up to concave down. So again, maybe you want to go back and look at your examples of concave up and concave down from our original example at the beginning of this video, and then come here and sketch the vertical lines where the concavity switches. All right, so the concavity is positive on this interval, right? We are concave up. Not sure why I'm writing positive. I should just write concave up. It is concave down on this interval. And it's also concave down on this interval. And then we're back to concave up on our final interval. So this makes it easy to tell where the concavity switches. We have a switch at B. We do not have a switch at E because the function stays concave down. We do have a switch at G because the concavity switches from concave down to concave up. So again, these are called points of inflection. These are where the function switches concavity. So let's talk a little bit more about how we figure out where these points of inflection are if we're not looking at a graph. So in our first example, we learned that f double prime is going to be positive when f is concave up, and that f sorry, I'm saying f prime, I should be saying f double prime. F double prime is negative when f is concave down. So if we go from something that's concave up to something that's concave down, we go from a second derivative that's positive to negative. If we go from concave down to concave up, we go from a second derivative that's negative to positive. So what do we think is going to be going on when we have a point of inflection? When it's neither concave up or concave down. That's what a point of inflection is. It's where the concavity is changing. Well, we have two options, right? In our first example, let me just real quick, I'll sketch these graphs rather small and quickly. So at the point of inflection, in this case, our second derivative graph, let me just finish marking these. Our second derivative graph was equal to 0, right? It changed from negative to positive. But remember, I said there could be another option, right? It's possible that our first derivative graph could look something like this instead. Right, it's possible for it to have a hard corner here, which means and in this case, our second derivative graph would actually, look something like this. Let me change it. It would look something like this, because the slope of the tangent lines to the left of, we can call this C, to the left of C are all negative and they're all the same. So we have a constant function for our second derivative. And for the first derivative, the tangent lines, as we move away from C to the right, they all have the same slope, they're just positive. So the second derivative would also be constant. So it's still changing from negative to positive, but it does not have a 0, right? It's not equal to 0. It's undefined. So the way we can go from negative to positive is we can either have a 0 in the second derivative, or we can have a second derivative that's undefined. But either way, it's changing signs from negative to positive or positive to negative. So f double prime is changing signs. And that's what we're going to fill in this box. And we just talked about it. This means that f double prime could either be equal to 0 or undefined at this point. It can't be positive or negative because that would infer that there's either a concave up or concave down appearance in our original function. But it can either be 0 or undefined. Those are our two options. Let's finish off this video by doing one or two practice problems with points of inflection. So we're going to do number 3 to start off with. We just need to find the x values where there are inflection points. And we also need to write the intervals for where the function is concave up and concave down. So pause the video, take some time to work through this one. We are also going to do number 5. So if you want to try to do both of those at the same time, that's fine. We're going to go over both of those before I end this video. All right, so the first thing I need to do is find my second derivative, right? Because that's what we're going to test for concavity and points of inflection. So I'm going to find my first derivative first. It's going to be equal to 3x squared minus 6x. Find my second derivative. It's going to be equal to 6x minus 6. So this second derivative is never going to be undefined because it's just a linear function. And so I'm just going to find out where it's equal to 0. And it looks like it's going to be equal to 0 when x is equal to 1. So this is my critical point of my second derivative. Both the second derivative and the original function are continuous everywhere. So I can go to positive and negative infinity. Remember, this is f double prime. Let's choose some test points. So f double prime of 0 is equal to negative 6. So my second derivative is negative on that interval. And f double prime of 2, well, that's going to be equal to positive 6. So my function is positive on this interval. Well, we've just found a inflection point, or a point of inflection, because the second derivative is changing signs at x equals 1. So we'll need to justify that. Inflection, and actually we'll say this way instead. We'll say f of x has an inflection point at x equals 1 because f double prime of x changes signs here. Now we also need to talk about concavity intervals. So we're going to say f of x is concave up on the interval 1 to infinity because f double prime of x is greater than 0 on this interval. And we can say f of x, not f prime, f of x, is concave down on the interval negative infinity to 1. Oops. Because f double prime of x is less than 0 on this interval. So this would be a complete answer. You have your justifications for the inflection point as well for the intervals of concave up and concave down. Let's finish off by doing number 3. If you haven't done it, go ahead and try it. If you have, you can just keep on listening. Same process, different function, right? This function may act a little differently though. Let's first find my first derivative. Got to use a quotient rule here. Derivative of my numerator is 0, so it doesn't matter what my denominator is, minus my numerator times the derivative of my denominator, which is 1, all over my denominator squared. So this is equal to negative 1 over the quantity x minus 3 squared. Let's find my second derivative. Derivative of my numerator is still 0. Then I subtract my numerator, which is really like adding it, right? Because it's a negative 1. Times the derivative of my denominator, which is going to be a chain rule. So let's actually put a bracket here. So I get 2 times the quantity x minus 3 to the first power times 1, because that's the derivative of the inside. It's a pretty straightforward chain rule. All over my denominator squared, so I get all that to the 4th. Which means if I simplify, I end up getting 2x minus 6 in my numerator all over the quantity x minus 3 to the 4th power. And now to check for critical points, I need to see where the function is undefined, where the second derivative, that is undefined, and where it's equal to 0. Well, it's undefined at x equals 3, because that's where my denominator is equal to 0. And now I can check to see where the function's equal to 0 by looking at my numerator. So I set my numerator equal to 0. and I actually get that x is also equal to 3. Now, here's the problem. It can't be undefined and equal to 0 at the same time. If our denominator is equal to 0, that takes precedence over our numerator, obviously. So we only have one possible critical point here, and that's at x equals 3. The function's not equal to 0 at this point. It is undefined at x equals 3, though. Now, here's the thing. When we are creating our little number line, where we list our critical points for f double prime, we also have to take into consideration what's going on with our original function. So our second derivative is undefined at x equals 3, but our original function is also undefined at x equals 3. So this is a point that we are going to place in our number line, but it's not going to be a possibility for a point of inflection because our original function is undefined at that point. It does not exist. So we're still going to use it to break up our intervals, but just know that at the end, it doesn't matter if the f double prime changes signs at this point, it cannot be a point of inflection. So let's go ahead and choose some test points and figure out the signs of our f double prime. So let's do f double prime of 0 for the left of 3. That gives me -6 in my numerator and -3 to the power of 4 in my denominator. This is going to give us -6 over +81, so we know it's negative. We do f double prime of 4. This could give me 2 in my numerator and 1 to the power of 4 in my denominator. That's a little bit easier. That is just going to be equal to 2. 1 to the power of 4, not 14. So now we can write our intervals of concavity. So f of x is concave down on the interval -infinity to 3 because f double prime is, and you can just say less than 0. You don't have to write it out using inequality notation. Just shorter. And then we can say f of x is concave up on the interval 3 to infinity because f double prime of x is greater than 0 on this interval. And again, no point of inflection at x equals 3 because f of 3 is undefined. All right, there's actually a vertical asymptote going on at x equals 3. We could figure that out by just looking at the function itself. Okay, we are going to call it a video. I know we're just over 30 minutes, which is fairly long, but there was a lot of material to get through here. So plenty of other things to work on. We'll go through some of it in class, but we're going to stop here. Enjoy the rest of your day, and as always, I look forward to seeing you next time.